All right, welcome everyone. This is the another installment of Exploring by the Seat of Your Pants. We've got a fantastic talk today by Daniel Devost from the Canada, France, Hawaii Telescope. I'll introduce him in just a minute, but let's see if I can introduce the classes that I can see here. Can Mrs. Let's see, Plur Duran's class hear me? No? Looks like they're having some troubles. Okay, give me 1 second. Let me see if I can sort them out. Okay, looks like they're having troubles. They've just contacted. I'll try inviting them again. Okay, so we've got, how about Mrs. O'Connor's class? Can you guys say a big hello to everybody? Wonderful. They're coming all the way from Thunder Bay, Ontario. Fantastic. Let's see, Mrs. Melvin's class. Can you guys say a big hello to everybody? Wonderful. Miss Melvin's class coming from Richmond, BC, over on the west side of the country here in Canada. And let's see, we've also got Mrs. Plur Duran from Saskatchewan still trying to connect. And so they should be coming here in a moment. So once they connect, we'll see them up and running. Otherwise, I'm going to introduce Daniel. Daniel Devost is the Director of Science Operations at the Canada, France, Hawaii Telescope. We're joining Daniel from the control room of the telescope, where he's going to explain a bit about how the telescope works and the mysteries of our universe that astronomers are trying to solve. The CFH Observatory hosts a world-class 3.6-meter optical infrared telescope, and the observatory is located on top of Mauna Kea. Is that how you say it? Mauna Kea? Wonderful. Yeah. 4,200 meters tall, and it's a dormant volcano in Hawaii, and the observatory itself is located in Waimea. So it's in Hawaii. I bet you their weather's better than we have here in Toronto and much of the rest of Canada.
That's correct.
I'll let you take it over from here. So tell us a little bit about your place.
Okay, thank you, Travis.
Thank you.
So hello, guys. So yes, as Travis said, I'm talking to you from the remote observing room today. Actually, this morning when I came in to prepare, the observer for the night was still here, finalizing his report. So you can see behind me all of the tools and instruments that we use. Everything, of course, is computerized, and we also use a lot of screens for the weather. So I'm going to start with the talk. Now I'm sharing my presentation. So Travis, do you see it?
Yes. Yes, it looks great. Thank you.
Okay, good. So as Travis said, I'm the Director of Science Operations. I'm originally from Quebec City, Canada. I got my PhD at Laval University, and I've been in the US for quite a while now. So I'll talk to you today about the Canada, France, Hawaii Telescope. So again, as Travis said, we're quite well located. So we're right in the middle of the Pacific on the Hawaiian Islands. Here you can see on the red square. Here's a zoom in on the big island. So on the red square, you have the whole archipelago of Hawaii, and to the left, you see the big island. In the red circle, here's where I am right now, so which is the town called Waimea, and the blue circle is the summit of Mauna Kea. So, and I have a purple link in there just to show you guys that we are completely operating from down here in Waimea. So we're about something like 80 kilometers away from the observatory, and everything is done remotely through the internet. Overnight, there's absolutely nobody at the summit. So the observer that was in when I came in this morning was finishing his shift, and it was by himself the whole night with nobody helping him either here or at the summit. So we're completely remotely operated telescope. So here's a picture of the summit of Mauna Kea. So there are 13 telescopes up there. The Canada, France, Hawaii telescope is the one that's smack in the middle. But there's quite a bit of astronomy that's being done up there on a nightly basis. So here's a picture of our outside dome. So you may notice this is not your typical backyard telescope. This is a 5-story building, and the telescopes sit on the top floor. And just to give you an idea, you can see at the bottom cars. So it gives you an idea of the scale. At the bottom, you have the different partners of the Canada, France, Hawaii telescope. So we're an international partnership. Basically, we're run by 3 institutions, CNRS in France, NRC in Canada, and the University of Hawaii here in Hawaii. But we also share time with the Chinese, NAOC. We share time with the Taiwanese and also the Brazilian. So we have people from all over the world that get data from us, astronomical data. So here's a view of the inside of the telescope, of the observatory. So you can see the telescope right there in the middle. As Travis said, we are a 3.6 meter telescope. So that's the size of the primary mirror. So our mirror is 3.6 meters wide. So that's a fairly big mirror, although in today's standard, certainly not the biggest mirror. They come up to 8 to 10 meters in size, up to 11 meters to nowadays. So we're a modest size telescope, but just to give you again an idea of the scale, if you look toward the bottom of the image, you can see someone on the floor of the observatory, and that's a person there. So it's a big, huge structure, the whole telescope itself. So I'll talk to you about instruments. So this, because that's a concept that's not necessarily well understood by people. Astronomers use instruments in order to do their science, and here at CFHT we have 4 instruments running. I'll talk to you about these instruments a little further, but first, just to tell you how it all started. So this is a picture, a depiction of Galileo observing basically the sky at night. So his instrument is his eye, and he recorded his data literally by taking notes. And this is how, you know, astronomy used to work. And these are the drawings, I'm sorry, of the moons of Jupiter. So if you take even a small size telescope and you look at Jupiter, you can see up to 4 bright little spots right next to it. These are the moons of Jupiter. And at the time of Galileo, we didn't know what these were. And basically what he was doing night after night, these are the drawings you see here, he was recording the position of each and every one of these dots, writing it on a piece of paper by hand. So, and that's how he figured out that these moons were actually going in circle around, were in orbit around Jupiter. And that's what led him to think that maybe it's not the Earth that's at the center of the solar system, but it's the sun and the Earth revolves around it. So very famous drawing here. So today we do it a little bit differently, quite frankly. We use cameras basically. So here's an amateur astronomer setup, and it is quite affordable in this day and age to be able to do that. So a lot of people do astrophotography. So the instrument in their case is not the eye and the pencil and the paper anymore, it's a camera. So basically you put a camera, you put it in focus, and you take a picture. And in astronomy, honestly, this is all we do. We take pictures of different things. We have different techniques to take all these pictures, but in the end, it always amounts to taking a picture with some sort of cameras. Of course, our cameras are a little different than the cameras you'll find in the market or on your cell phone or anywhere like that. So we have 4 instruments, and astronomers like to name their instruments. So our 4 instruments are named Megacam, WearCam, Espadon, and CITEL. So these 4 instruments basically are put on the telescope at different times of the year. So here's Megacam, which is, as you can see, a big camera. So it's 6 meters tall. So just again to give you an idea of the scale, here's a 1.8 meter person right next to it, more or less. So it's an enormous camera, and it takes really large pictures of the sky. So to the left, you have an idea of the field of view of megacam. So what I call field of view is, you know, the field that we take a picture of. So when you look into a camera, a regular camera, and you take a picture, you see the field of view that you're gathering. So here, it's the same. It's a 1 degree field of view. That doesn't sound really big, but in astronomy, that's a pretty big field of view. So that's 4 times the size of the moon. So in one picture of megacam, we can put basically 4 times the moon there, which for astronomy is quite big. So here's on the right, you can see the detectors that we use for this camera. And again, it's not your tiny detector in a phone camera. It's a big array of detectors, basically. And but essentially, these detectors are more or less the same than what you find in your camera. It's the same physical principles of transforming light that's coming into a camera into electronic impulses that can be collected and then further analyzed. So the principle is the same. The big difference for the astronomy cameras is that they are big usually. So this one here is an array. Megacam is an array of 40 detectors that you can see there, and you can see somebody's hand. So it's quite big. So also Megacam is a prime focus instrument. I'll come back a little bit with that later in the talk. But the prime focus here, the camera is all the way up in the air, something like 100, 150 feet up in the air, and there's only one bouncing. So the light comes and hits the primary mirror down here, and then goes up to the camera where it gets captured. So our other instrument is called WIRCam. It's also a prime focus instrument, and it's also a regular camera. The difference that it has, it's an infrared camera, and it's also a little less wider field of view. The field of view of WIRCam is about 1/4 of that of Megacam. So it means that we can take a picture of about the size of the moon, more or less, with WIRCam. The big advantage of an infrared camera is that you record heat instead of recording what you usually see with your eye. So Megacam records the light that you see with your eye, but WIRCam records infrared light, which is light that you cannot see with your eye, but it gives you an idea of the heat of whatever you're recording. So you have a good example here, 2 glasses recorded in the optical light, which is a regular camera, which is the light you can see with your eye, and you can't make any difference, you cannot differentiate the temperature between these 2 glasses. However, if you take an infrared picture of it, you can see clearly that the red glass is hotter than the blue glass. So this is one big advantage of infrared, is that you record the temperature. You can measure the temperature. Another advantage of infrared imaging is you see it at the bottom. There's a person holding a trash bag with his hand in the trash bag, and in optical, you cannot see it. You cannot see the person's hand. But if you look at it in the infrared, you see perfectly well the person's hand. So that's another advantage of infrared over optical imaging. Optical meaning light you can see it with your eyes, is that you can see through some things that you cannot see with optical imaging. So infrared imaging is a different regime, and it allows us to do different science than what we do with optical imaging. So our third instrument, espadon. So espadon is a spectrograph, and it's French for swordfish, and it's a French instrument. So it's a little more involved in terms of complexity because it's a spectrograph. I'll explain to you what we do with a spectrograph in the next slide. Here you have, on the right, you have the capture unit. So we call it the polarimetric unit. So it captures the light, has a polarimeter there, and then it sends the light through a fiber, basically, which you see in blue. And that blue represents something like 30 meters of fiber that goes all the way down to a different floor of the observatory, the third floor of the observatory, to be precise. And this light that comes out of the fiber is recorded by the spectrograph, which is essentially, again, a camera, but a little more involved in terms of design. It's not direct light. So here's what I mean by that. So you have a cartoon here that shows the light that comes from a star, any star, could be the sun, and you send it through a prism. So basically, the prism, what it does for you is splits the light into its colors. I'm sure you guys are aware of this phenomena. Something you see also in rainbows. So in rainbows, what happens is that the light comes in from the sun, hits some droplets of water that are suspended in the air, and the droplets of water act like the prism and spread the light out, and you can see basically the rainbow. So the rainbow is basically the spectrum of the sun that you can see with your eyes. So with a spectrograph, what we do basically, we put an optical element, we control how we spread the light, how we split the light in its colors, and we record it. So here I have just a cartoon of how we record this rainbow, basically. So with a spectrograph, what we do essentially, and this is all you need to remember of this, is that we record the rainbow of stars. That's literally what we're doing. However, again, we can record parts of the rainbow that's not visible to the human eye. So we can go into colors that are invisible to the human eye and then do different science with it. So Espadon does record a lot of its light that's outside of what you can see with your eye. And the last instrument is called CITEL. So CITEL does both, basically. So I talked to you earlier about a camera that takes pictures and about a spectrograph that splits the light and records the rainbow. With CITEL, we actually do both. It's quite a novel instrument that was developed at Laval University by a company called ABB Bowman in Quebec City. And actually, this instrument was on the telescope last night, and we're taking it off tonight. We're replacing it by another instrument. So on the left, you can see the instrument itself. It's fairly big. It's about the size of a person in height. And on the right, you can see a model of the telescope with the instrument on the telescope. So it's a secondary focus instrument. So basically, the light comes on the primary mirror, bounces up on the secondary mirror, because we don't have a camera up there when we have set on the telescope, and then is recorded by CITEL. So CITEL is quite a complicated instrument, honestly, and it's a one of a kind. It's something that's really hard to do. It's something that's based on the principle of something called the Michelson interferometer. I won't go into the details on that, but what you need to remember from that is the colored picture that you have on the lower right. So you have a blue picture, a red picture, a green picture, dark green, and a lighter green picture. So basically, this is how the instrument works, is that it records different colors simultaneously just by taking one image. So it's extremely powerful to do that. And right now we're in the phases of final testing of this instrument, and it should have its first official launch of this year, of 2016. So we're very excited by this instrument. It gives us quite a bit of new capabilities. It's unique. We're the only ones who can do that sort of imaging with it, imaging and spectroscopy at the same time. So we're very excited about it, and looking forward to have it work for many years to come and produce a lot of science. So speaking of science, I'll just outline you a little bit some of the science that we do here at CFHT. The type of science that has the highest public impact. We do a lot of things, but there are several things that are of public interest, and people are excited by those. So I'll talk to you about those. So we do a lot of work on the dark matter, dark energy thing. So as you may know, we know very little of our universe. So this pie chart here shows you what we know, which is the red area. which is the 4% normal matter. So what that means is stuff that makes you and me. It's the atoms, the hydrogen, the iron, the whatever we know. When we explore the universe, we see these components only in 4% of the universe. So there's one component that's 21% of the universe is the dark matter. So that's the blue part in this pie chart. So dark matter is something that we see indirectly, and we've never really seen a real image of dark matter, because then that's why we call it dark. It doesn't emit any light, but we have secondary clues that it's there, and I'll show you one of those. And here at CFHT, scientists have developed quite an involved technique using megacam to detect dark matter, detect the presence of dark matter. And 75%, the biggest chunk of the pie chart, is dark energy, and it's something, again, that astronomers don't understand. We detect it indirectly. We don't know what it is. There's several theories that try to explain the origin of dark energy, and it composes 75% of the universe. So it's a huge component of the universe. And basically what I mean by dark energy, it's a force that pushes on the universe and makes it accelerate. So it's really, it's a force in itself. So it's something quite puzzling. So here's a picture of detection of dark matter that was done a year or two ago, something like that. So basically the blue part in this picture is where you infer that the dark matter is. So, and basically what they do is that they use this image and they look at distortions of the image in the image that they think are created by dark matter. I won't go too much into the details, but matter bends light, basically. This is something that Einstein found a while ago, and this is basically the application of this theory. You basically look for deflections of light in an image like this one, and what you get in the end is a map of the dark matter in a certain area. So that's what I mean when I say indirect detection, is that it's not a direct image of dark matter. There's no real light coming out of there, but you can infer its presence by looking at galaxies and things around this image. So the other one that I'm going to talk about is extrasolar planets. So it's the search for life, basically. So astronomers are very interested in that, and quite frankly, this field has boomed literally in the last 3 to 5 years. So here's what I mean by that. So this is the number. I apologize for the small writings on the X and Y axis. But in the X-axis, you have the time starting in 1988 all the way to 2014. And on the Y-axis is the number of exoplanets that were discovered on a specific year. So you can see that starting in 2009, 2010, the number of exoplanets discovered has risen to peak in 2014. And I don't have the number for 2015 yet, but I'm certain it's higher. And basically, we're finding more and more planets around other stars. And the idea is to find life around these planets. The arrow points to the first discovery in an extrasolar planet, which was done here at CFHT in 1989. So that was a difficult detection. Nobody was really sure that it was a planet or not. But now today, instruments are way more sophisticated, and we can easily detect this signal that was really hard to detect in 1989. But it turns out that the signal they detected in 1989 was actually really a planet, and was the first discovery, basically, of a planet outside of the planets of the solar system. So what we're looking for in these extrasolar planet searches is obviously a planet in the habitable zone of a star. And what we mean by habitable zone is where the temperature is warm enough to allow liquid water on the surface of the planet. So you can figure that out by knowing what type of star it is, what type of star the planet orbits. And here you have a cartoon depicting that. So you have the red area, the planet is way too close to the star, the temperature is too hot. If there is water on the surface of that planet, it'll be gaseous, it'll be water vapor. And it doesn't mean that life cannot exist there, but life as we know it cannot exist. That planet is going to be dry. There will be no water on its surface. In the green area, this is where light can be, water can be liquid. And there, when we find planets in these areas, we're hoping that there might be life on their surface. And if you look at the too cold area, the planet is too far from its star, and all the water that would be found on the surface would be frozen, basically frozen planet. So again, it doesn't mean that there's zero life, but life as we know it here on Earth would be very difficult, basically. So this habitable zone here depends on the type of star that you're looking into. So at the top, you have the sun on the left-hand side, and you can see here, if you go toward the left, you have Mercury, Venus. So you can see that the Earth and the shaded blue, the blue area is the habitable zone of the sun. So you can see that Venus is a little is right on the edge. Mercury is outside and it's too hot. Earth is right on, and Mars also is on. That's but we've never found liquid water on Mars. We found frozen water, but never water in a liquid state. So there's other things that go into this process. And if you look in one star that has 4 planets discovered around it, Gliese 581. So it has 3 planets that are close, Gliese 581c, which is close to the habitable zone, and then D is close to the outside of its habitable zone. So this is how we try to figure out how there can be life on a planet. So D might, but it might be cold there. C might have life, but it might be a little hot. So, and there's a lot of these planets that we're finding out of the 1,000 now, over 1,000 now that we found. And this is 6 months old, so I'm sure there's more than that. But this is just a list of the planets that can be found, that are found in the habitable zone of their star. So these planets are potential candidates for life. Basically, there's a lot of other things that come into account, but these are the most promising candidates. And these are artist representation. We don't know what these planets look like really. So in conclusion, I'll stop here. So science at CFHT goes from stars in our neighborhood to very distant galaxies using now 4, I forgot to correct that, 4 state-of-the-art instruments. And CFHT helps us understand basic questions about our universe and the planets around other stars. So I'll stop here.
Wonderful. Fantastic. Thank you very much. I think we'll have a few questions from some of the classes here. So I'll start with, let's see, Mrs. O'Connor's class. Let me turn on your mic. Do you guys have a question for Daniel Devost about the work they're doing up there in Hawaii?
Yes, we do. Thank you. Mason.
Hello, my name is Mason, and I'm wondering what your favorite discovery has been.
My favorite discovery? That's a good question. Let me think for a second. Well, it's a discovery that that was done by CFHT, and basically when the guys were able to get together these lumps of dark matter using images at CFHT, that was one of my favorite things that we were able to find here, because that opened up a whole new area of science, basically. So we were able to see and see indirectly what we couldn't see before, and to me that was quite important. There's several other things, but that's one of them.
Great, thank you.
Thank you very much.
What about Mrs. Melvin's class? Do you guys have a question for?
Yes, we do.
Wonderful. Come on up.
How long did it take to build the telescope? Were there any errors or confusions?
Oh, very good question. Yes, yes, there were errors, and there always are. And it took about 10 years to build the whole thing. So construction started in 1969 or 68, 69, and finished in 1978 or 79. So it took a long time to build the telescope, and especially since it was the first one of this size that was built on top of Mauna Kea, so all the infrastructure was not necessarily what it is today. And there were, problems with the telescope, and this is why we take a long time to test it and make sure that everything runs well, and there's adjustments to be done, and things that need to be fixed and repaired because they're not quite right. So that takes a year or two of work before you get it efficient and working well. So yes, there were several little problems, but they were attended. Nothing like I'm sorry if you nothing like the Hubble though. I don't know if that's what you were referring to in your question, but we had nothing like what the Hubble Space Telescope went through.
Wonderful. Thanks, Daniel. Let's see if we can grab another class here. Is this Mrs. Stabile? Did you make it in?
So it's 5 hours earlier.
Wonderful. Thanks, Daniel. You guys have a question for Daniel?
What do I do?
Oh, hello. Just seeing if you guys have a question for Daniel.
We do.
Yes, we have a question in Mrs. Stabile's class.
Yeah, Lily. Where's the camera? Right here.
There we go. What's your question?
Lily, question.
How did you get the electricity up by the telescope?
I'm sorry. Can you repeat the question? I didn't hear.
How did you get all the electricity up there?
How did we get all the
Electricity.
Oh, okay. Yeah, so that's a problem. It's a good question. All the telescopes have been in Hawaii for a long time, 40 years. So now electricity is all the way up there, but it's just a matter of running the wires up the mountain. So right now we have all the amenities, but it took some work at the beginning to get it there, and now we have quite a bit of power up there. The telescopes are very demanding in terms of electricity. So just to give you an idea, our electricity bill at the summit is $30,000 a month. So, and we're not one of the more expensive. So it's just a matter of bringing a wire up there.
Wonderful. I'm going to check with one of the classrooms that it seems like their camera's off. Let's see if they are here. This would be Mrs. Pleur-Duran's class. Do you guys have a question? No, it looks like we can't hear him. So we'll go back to Mrs. O'Connor's class. See if you guys have a question for Daniel about telescopes or space.
Hello, my name is Tyler, and I am wondering do you believe there is life on other planets?
Oh, very good question. Thank you for asking it. So yes, I do believe there's life on other planets. To me, it's just a question of time that we discover it. Now, when I talk about life, I talk about, you know, a cellular organism, a tiny bit of life which has never been found yet. We've never even found a cell or evidence of cellular activity on any other planet, on Mars or the planets of the solar system and planets outside of the solar system. However, we're discovering a lot of planets outside of the solar system, and that was expected, and there's a lot more out there. Just the sheer number, to me, tells me that there is life out there. It's just a matter of finding it. Now, that said, is this life close to us or far from us? That's a big question. And life close to us may be very rare. But if you look at the whole universe, it's got to be there somewhere. And most astronomers think that, too, is that there is life out there. It's just a matter of finding it. And we don't know really how much there is around us. Because keep in mind, when we look at planets around other stars, it's just the stars right around us. They're not very far from us when you look at it compared to the whole scale of our galaxy and of the universe as a whole. So the probability of finding life there may be small, although I think we will find it. But in the whole universe, it's a certainty to me. There is life.
Thank you.
You're welcome.
Let's go to, let's see here, if we could go to Mrs. Melvin's class again, if you guys have another question.
Yes, we do.
When was the last time the Mauna Kea erupted, and when do you think it will erupt again if it ever does? Isn't it dangerous to put the telescope there?
Good question. So I think, I'm not a volcanologist, but I think it was several thousand years ago that the Mauna Kea erupted for the last time. The number I have in mind is 5,000 years. So it was a while. It's been a while since it erupted. Now the volcano is classified by volcanologists as a dormant volcano, meaning that there's still a puddle of magma under the volcano, but it's not active. So the chances of it erupting again are fairly small, although they're not zero. So we feel it's fairly safe to be up there, although the probability is not zero, but we think it's really small that it will erupt again.
Thank you.
Thank you.
Thank you.
Stop touching my hair. Do you have a question? Say your question, Kurt. Ask your question.
Sergeant? Hi, my name is Kurt, and I was wondering, what are you guys currently looking for?
So right now there's a lot of work that goes into we have one instrument that does that really well.
What are you currently looking for as a question?
Right now there's a lot of work that goes into
Out. Go back. Go.
we have a little bit of a lag.
Out.
We're also looking
What are
at
you currently looking for?
dark energy. We look Did you guys hear the answer?
Sorry, Daniel. Yeah, we had some technical difficulties. Would you mind repeating the answer to the question?
Yeah. So nowadays we look at try to find planets around other stars quite a bit, and also trying to map dark matter and dark energy. There's a lot of work that's being done toward that these days here at the telescope.
Cool. Let's see. We've got Mrs. Stabile's class. Do you guys have another question? Another question for Mrs. DeVille's class?
Oh, here we go.
Go ahead.
How do you get your resources up the volcano?
Okay, so the question.
Can you repeat the question, please?
Can you repeat the question?
It's so muted.
How do you get your resources up
I can hear you.
So it looks like the question was, how do you get your researchers?
How do you get your resources up the volcano?
Oh, okay. Well, we have a road. So it takes about an hour. We have to have 4x4 trucks to go up there. But basically, it's a road that goes all the way up the mountain. We call it the Summit Road.
Cool, wonderful. Do you have another minute for a couple more questions?
Sure.
Wonderful. Let's go back to Mrs. O'Connor's class. Let me get your mic on here.
Andrew.
Go ahead, Andrew.
Hi, my name is Andrew, and my question is, why is the telescope in Hawaii?
Oh, very good question. Glad you asked. So, as I was showing you in my first or second slide, you can see that we're in the middle of the Pacific Ocean. So we're surrounded by a big, huge, cool ocean. So that means that it cools off the air above Hawaii, and that makes the turbulence above Mauna Kea really, really small. And when I talk about turbulence, is when you look up at the sky and you see the stars that twinkle. The more they twinkle, the more turbulence there is. And here on Mauna Kea, there's less of that, way less of that, and it's because we're in Hawaii, in the middle of the ocean. And this is something we call image quality, and this is something that's really important for astronomers. We really want to have the best image quality possible and the least amount of twinkle in the stars possible. And we can actually measure that twinkle, and basically it's one of the best sites on Earth here for that. If we were to be at the same height, let's say on the mainland or in Canada, the twinkling wouldn't be as low as it is here. So that's the main reason why we're here in Hawaii, is that the turbulence in the atmosphere is very small here. It's lower, much lower compared to most sites in the world.
Thank you.
You're welcome. Any questions?
Yeah, go ahead.
How far can a telescope see?
So we can see something like 10 to 15 billion, 10 to 13, I'm sorry, billion light years out. So when it's that far out, we talk in light years. So a light year is the distance that light travels during 1 year. So just to give you an idea of the scale, light takes 8 minutes to go from the sun to the Earth. So it takes 8 minutes when the sun emits a photon of light to reach Earth. So, and again, the closest star is 4 light years from us. So if we were to travel on a ray of light and travel for 4 years, we would go to the closest star. And light travels really fast. So we see something like 10 to 13 billion light years out. So that's really far. And these are the faintest objects we can see in our images.
Thanks.
Okay.
Let's try back in Saskatchewan here, Mrs. Pleur Duran's class. Do you guys have a question? Let me get your mic on. There we go.
My name's Lee, and my question is, what is the most recent thing in the telescope?
I'm sorry. I didn't hear the question. Repeat it.
My name is Harry, and what is the most recent thing you have found looking through the telescope?
I'm going to get very technical here, but I came across a paper recently using different data to figure out that there was a lot in the filaments of the universe. So, model the whole universe.
Daniel, there's some feedback. If you mind just hanging on one moment.
Okay.
If everyone could please make sure their mic is off beside Daniel, and then we can hear his response.
Can you hear me?
We sure can. Go ahead.
Okay. So what I was saying, I'm going to get a little technical here, but when we do a model of the whole universe, the universe as a whole, it comes out to be filaments all over the place. And I don't have a picture to show you, but this is one of the findings that was done a while ago, basically. So we see the universe as a bunch of filaments, literally. And it was found recently with CFHT that these filaments actually hold a lot of matter like us, the 4% that I had in your pie chart at the beginning of the talk. This matter is found in these filaments, and that was an important discovery. That's something that's really hard to do, prove that there is matter there, regular matter, and we think that's the stuff that forms galaxies and eventually stars. So that was a big discovery that was done recently here, using images here. There were several telescopes that were involved in that, but CFHT was one of them.
We'll try Mrs. Stabile's class again. Do you guys have another question? Another question from Mrs. Stabile's class? There we go.
Yes.
Great. I can hear you.
I'm Claire, and how many hours a day do you work?
So the telescope here is open 24 hours a day. So we have somebody during the day here. I work during the day. I do a 9 to 5 thing. But we have someone that comes here. So the telescope here is open 24 hours a day. So we have somebody during the day. Somebody I work during the day.
Mic's still on.
So did you guys hear the last part? So I work from 9 to 5, mostly. Sometimes I work late at night. But we have the telescope here, the observatory is open 24 hours a day, 7 days a week, 365 days a year. So there's always somebody working here.
A personal question, I probably shouldn't ask that.
Does Mrs. O'Connor's class have another question for Daniel?
Yes. One more. Yes, we do. Last one.
Hi, my name is Brennan, And my question is, have you ever discovered a new planet or galaxy? How do you decide what to name them?
So, yeah, here we at CFH we find new things all the time, especially in galaxies, and the way we name them is basically a number. So we add a number to whatever catalog it comes from. So what we do, when we find new things, the scientists put them in catalogs and they give them a number. So this is how their galaxies are assigned a name. The name is literally a number. And a galaxy can have several numbers. So it can have several names. They may all refer to the galaxy, the same galaxy. So it's pretty boring. We don't have nice names for everything. It's mostly, you know, a letter saying the name of the catalog, and then a number, a sequence of numbers for each object that's in that catalog.
Thank you.
Thank you very much.
Thank you.
Wonderful. If we have Agnes, let's see, Mrs. Plura-Duran. If you guys haven't asked many questions, do you guys have a question?
Yes, Lene. Yes, we do.
Wonderful.
Lene?
Hi, my name's Lene. Have you found any other life forms on other planets?
No, not yet. We're still hoping to find some. If life is found, it won't. I don't think it'll be CFH that will do it. Although we may have an instrument to enable us to do that. But for us, it's a very difficult measurement. The measurements that are going to be needed to have proof of life in another planet are really space observatories. And there's one that's going to be launched in 2018 that's called the James Webb Space Telescope. It'll literally replace the Hubble telescope. And this one has a good chance of having proof of the existence of life on another planet. It's a very difficult measurement to make. So I doubt it would come from CFHT, but who knows? But it's most likely to come from space.
Thank you.
Thank you.
Wonderful. We also have Mrs. Melvin's class. Looks like you have another question there.
Yes, we do.
What's a typical day in the observatory headquarters? What's the daily routine?
The daily routine. Okay, so it starts. The first thing that happens during the day, most of the time, is the observer that has spent the whole night observing sends his report. So they type a report and they send it in an email to everybody. And now we look at what problems have happened, and then the engineers go and tackle these problems. So they may go up to the summit, try to fix something, and things like that. In parallel, there's a scientist that prepares the next night. So during the day, probably midday, that scientist prepares the observations for the upcoming night, and then sends again an email to everybody telling them, okay, this is what we're planning on observing tonight. And then in the evening, the observer who slept the whole day, because remember, he left early in the morning, he slept the whole day, and then he comes in and then looks at what happened during the day, looks at the planning of the observations, and starts observing around, these days, 6:30, 7 at night, all the way to 6, 7 in the morning. So this is a typical day at CFH, you know, fixing what's at the summit, what problems that happen at the observatory at the summit, and preparing the observations for the upcoming night. And of course, observing.
Wonderful, thank you. Do you have time for one more question?
Yeah, sure.
Let's go back to Mrs. Plura-Duran in Saskatchewan. Do you guys have another question? Let me see if I can get your mic on. Just give me a moment.
Yes, we do.
There we go.
Hi, I'm Brooklyn. What's your favorite instrument to use?
Oh, I have to say that it's the latest one we got. It's called CTEL. So it was built at my home university by a good friend of mine. The scientist that is the principal investigator on it is called Laurent Driesen. And this is where I did my thesis. So it's an instrument that comes from Quebec City. So I have, a special attachment to it, and it's working really well. And also, it does science on my field of science, which is metals in the universe, measuring the amount of metals in the universe. So definitely my most favorite instrument.
That's wonderful. Well, thank you very much. I'm going to let all of you, I'm going to turn all your mics on so you can all say thank you to Daniel Devost for taking the time to show us his telescope in Hawaii. So feel free to all shout out a big thank you to him. Wonderful. That was amazing. I learned a lot on that talk. Thank you so much, Daniel. The telescope there looks amazing. Your work you guys do is amazing, and we really appreciate you taking the time to hang out with us again with Exploring by the Seat of Your Pants.
No problem.
All right.
You're welcome. That was my pleasure.
Wonderful. Okay, bye, everybody.
Bye. Nice talking with you.